So this section is based on trigonometry, but in a different light than what you're used to. When we do sine, cos, and tan, we are looking at ratios of side lengths in order to find out what the angle lengths, or angle, not lengths, but sizes are. All right, and we know a couple things, that if the side across from the largest angle will be the largest side, the smallest side and the smallest angle across from each other. If two sides are equal, then the angles have to be equal across from them. Well, sine, cos, and tan all come from ratios of the sides. We're comparing the lengths of sides to get the angles. All right. Now, when we apply this to a grid, which is what we're going to do, and this is going to be, there's no real easy way of doing it. We just have to work through it and plug through it. Look at page 56. An angle theta is in standard position when the vertex of the angle is located at the origin on a Cartesian plane. The initial arm of the angle lies on the positive x-axis. Okay, so the first thing that you need to know is this, is that an angle is in standard position, and it can be anywhere along this, as long as two very basic criteria have to occur. The first is the vertex is at the origin, and the second is that one arm is along the positive x-axis. Okay? So that's the first. Now, standard position can occur in the first quadrant, like that. It can occur in the second quadrant, in which the angle is this way. The angle in standard position will always be made in a counterclockwise direction. So the angle in the third quadrant would be this angle, and the angle in the fourth quadrant becomes that angle there. Okay? So that is when we say that an angle is in its standard position, when the first arm of it, the initial arm, is on the x-axis, and we work counterclockwise around to get the angle. All right? Measure the angle theta in a counterclockwise direction from the initial arm to the terminal arm. The quadrants of the Cartesian plane are labeled with Roman numerals, also in a counterclockwise direction beginning from the positive x-axis. We know that already, but let's do it anyways. Okay? So our quadrants are always labeled 1, 2, 3, 4, right? Okay. There's so many things that we have to get out of this, so it's going to take a little bit of time here. The angles in the first quadrant occur between 0 degrees. We'll let the angle be theta, that's this guy right here, and 90 degrees. The angles in this quadrant will measure between 90 degrees and 180 degrees. Down here is 180 degrees to 270. And down here is 270. (360 degrees). Okay? So think about how this looks. If I go from here to right here, what is that angle? It's 90 degrees. And then if I keep going to here, it's 180, 270, and 360, right? Okay, so it's not anything that you don't already know. Now, the second real important piece of information that you need to know is the angle that is made to the x-axis, always to the x-axis, is referred to as our reference angle. So from here to here is our reference angle. From here to here is our reference angle. There to there, reference angle. Here to here, reference angle. Okay? So these, theta r, is referred to as our reference angles. And they are always made with the x-axis. Okay? Now, you'll understand as we get going why it's so important. One of the reasons is, if you remember to apply when we did ambiguous triangles, so to find out if there was 0, 1, or 2 triangles, right? We found out that the sine of 150 happened to be the same as the sine of 30 degrees, correct? Okay? This is where this is all going to come from. You're all going to understand it from drawing our angles on top of this. Well, this reference angle of 30 degrees here, so the sine, that would be the sine ratio of y over, opposite over hypotenuse. Same thing here, opposite over hypotenuse. The reference angle here is 30 degrees, which makes this 150. And so that's why the sine of 150 and the sine of 30 degrees is actually the same. Okay, and that's because your reference angles are the same in both cases, they're both 30. So we'll talk about that a lot more after the fact. Okay, so first things first. An angle is in standard position if your initial arm is on the x-axis, your vertex is where the origin is, and it opens up counterclockwise. So there's the first thing. So standard position. Okay? The arm itself is called the terminal arm. Alright? So it's called terminal arm. So 3 words so far. Standard position, terminal arm. Okay? Reference angle is the angle always made with the x-axis. Your quadrants, 1, 2, 3, 4, we know that from probably grade 6 or 7. And then your angles are always made counterclockwise. Therefore, from here to here is 0 to 90, 90 to 180, 270, excuse me, 180 to 270, 270 to 360. Okay? So far, so good. Any questions yet? All right. Now, our next primary focus. Up to this point, you have been using your calculator to find out the sines of the angles, the cosines of the angles, the tans of the angles. Okay? Each time you use your calculator, you're getting a value that is sometimes rational, sometimes, or they're always rational, sorry. Sometimes a whole number, sometimes it's a decimal, and sometimes it's an irrational number in which you have a non-repeating decimal. What we are going to do is we are going to study 2 particular triangles so that we can, by the end of grade 12, solve the exact value of a pile of different angles, all based on this Cartesian plane. So to start with, I'm going to show you the very basic, okay? The very basic. And then we'll understand why we're doing this after the fact. Here's triangle number 1. All right, before I go any further, one of the things that we are going to look at is this whole thing becomes what we call a unit circle. All right? The reason we call it a unit circle is because the radius from the origin to the outside of the circle is always going to be 1. So we're going to have a distance from 0 to 1 anywhere around the circle. Okay? Now, the first of the 2 important triangles we're going to look at is the 30, 60, 90 triangle. Now, the one thing that I will always refer to if you get stuck is what is the sine of 30 degrees. Okay? It is the one thing when we do this trig now and in grade 12 that you have to absolutely remember. the sine of 30 degrees. Because when you get into grade 12, there is zero calculator work for this. You do all of this from memory. Okay? The sine of 30 degrees is a half. That means that your ratio of your side opposite over your hypotenuse is 1 over 2. The sine of 30 degrees is 1/2. Okay? Sine 30, you punch it into your calculator, you get 0.5. You need to remember that the sine of 30 degrees is a half. Don't ever forget that, because we're going to refer to it over and over and over again. All right? What does that then make this side? Anybody know what the length of this side is going to be then? Well, what do you think? 1.5. Anybody else want to try? Anybody have any idea how you find it? How about that? 2 squared subtract 1 squared. 2 squared is 4. 1 squared is 4 subtract 1 is, and then square root it. You weren't far off. You weren't far off. I'm not going to use a calculator though. I'm going to leave it as the square root of 3. By leaving it as square root of 3, I am referring to that as being an exact value. Because if I do use the calculator, it gives me an irrational number, a non-terminating, non-repeating decimal, and at some point I have to round it. So I'm going to leave it as just square root 3. So now, this allows us to find 6 ratios that we want to know without using a calculator. All right. What is the sine of 30 degrees? 1 over 2. Most important thing you're going to need to remember at all times, because this gets you to this triangle, which is what we're going to use over and over and over again. We want to know every 30 degrees around that unit circle, so the sine of 30, 60, 90, 120, 150, 180, 210. We want to know all of them, all the way up to 360. We have to know that. Okay? What's the cos of 30 degrees? Square root 3 over 2. What's the tan of 30 degrees? 1 over square root 3, which we are going to change to root 3 over 3. Okay, we're going to rationalize that. Don't worry about that right now. We have some radical work we have to do that we got to come back to. What's the sine of 60 degrees? It's the sine of 60. What's the side opposite of 60 on my triangle? Yeah. Side opposite's root 3, right? Hypotenuse, 2. What's the cos of 60 now?
1.
What's the tan of 60? Root 3 over 1. Those 6 values you're going to have to know without using a calculator, without doing anything. All you have to do to remember it, draw the triangle. You draw the triangle, gives you 1 over 2 and 30 degrees, because sine is opposite over hypotenuse. And at that point, you should be able to fill all of that in. And you know what? You now know the sine of 150. It's 1/2. You know the cos of 150. 3 over 2 with a negative sign. Okay? You're going to be able to go all the way around a circle just using those 6 values there and writing them in. These are actually going to be coordinates around the circle. There's one other one that we do now look at as well. Okay? And that is this guy. That guy, okay? All right, so looking at this, sine of 45 degrees, opposite over hypotenuse. What is that? What's the side opposite of one of the 45s? Tell me? 1. It's the same in both cases, correct? Where's the hypotenuse? Square root 2, across from the 90 degrees. So what is the sine of 45 degrees? 1 over root 2. Again, if I rationalize it, meaning that I take times the top and the bottom by root 2 and root 2, I change it to root 2 over 2. What's the cos of 45 degrees? One over square root 2, it's the exact same thing. And what is the tan of 45 degrees? What is it?
1.
1. Those two triangles are going to be used over and over and over and over and over again. And if you ever run into a problem, you draw the triangles and it bails you out. So we do need to know this, and we will get there. Okay? But for today, we're not there yet, but they do show it to you, so we'll get back to that. Okay, look at page 57. Follow in your book, please. Sketch each angle in standard position. State the quadrant in which the terminal arm lies. All right. 80 degrees. For theta equaling 80, the angle lies between what? Which angle? 0, 90. So write that in. Which quadrant is it in?
First.
That's right. First quadrant. Anywhere right about here, right? There's my 80 degrees. Okay. So it's between 0 and 90. How about 120? Between what? 90 and 180. Which quadrant is that? Second quadrant. And that is somewhere right there. Okay? How about 266? Which quadrant is it in? Third. So that's between what angles?
180 and 270.
Excellent. Good work. No, somewhere down there, 266. Anybody not know how to get all of that? Again, you start at the x-axis and you go counterclockwise to get it. That's all there is to it. Okay? Kara? Tough day? Okay. You haven't heard it in your book though? Now we're here at least. Pay attention, okay? Alright, determine the reference angle. For each angle, sketch the angle in standard position, label the reference angle, theta r. Theta is 315 degrees. Okay, so which quadrant is 315 degrees in? Fourth quadrant. Okay, so agree, it's down here, that's 315 degrees. Where is my reference angle located at all times? To the x-axis. That's exactly correct. So how would I then find out what my reference angle is right here.
Subtract that from 60.
Yes, you would. Subtract that from 360, which gives me 45 degrees. There's my reference angle. Very easy stuff so far. Okay, so, everybody understand this? Right. Okay, in this quadrant, I can get, actually just wait, I'm not gonna go there yet. Oh wait, I do have something I wanna show you, but not yet. Okay, how about theta equaling 201 degrees? Which quadrant is 201 degrees?
30.
Third quadrant, somewhere over here. So that is 201 degrees. How do I get my reference angle here?
Subtract 270.
Subtract from 270? Okay. So if I subtract that from 270, I get 69. Is that this angle right here?
No.
Which one is that? That's this angle right here. Agreed?
Subtract from 180.
Yeah, not from,
Subtract.
but subtract 180, right? Because from here to here, if I were to stop right there, that's 180 degrees, right? So then I gotta carry on. So 201 subtract 180 gives me 21 degrees, which is my reference angle.
How do you know your reference angle is one on that side?
It's always made with the x-axis. Always. Okay? So I showed you that here. Reference angle, always made with the x-axis. Okay? It's a good question. A really good question. Alright? So far we're okay? Determine the measure of all angles in standard position between 0 degrees, less than theta, less than 360 degrees, that have a reference angle of 35 degrees. Okay. So, I want all the angles in all four quadrants, because it said from 0 to 360, that have the same reference angle as 35 degrees. So in quadrant 1, what's the angle in quadrant 1 that has the same angle as 35 degrees? 35 degrees. Right? Quadrant 2, I want to find out what this angle is if my reference angle is 35 degrees. 180 subtract 35, which gives me 145 degrees. Maybe I should wait. Down here, reference angle, 35 degrees. What is this angle? 'Because 180 plus 35. Very good. So that angle, 215 degrees. Reference angle, 35 degrees. What is this angle? Pardon me?
325.
325, because you did what? Subtract the what? Sorry?
35.
This is 325, right? Okay. So, add this to your notes. Add this to your notes. The reference angle in the first quadrant is just the reference angle. So to find out what the angle is, you're just going to have the reference angle. In the second quadrant, I take 180 degrees minus my reference angle to get this guy. In the third quadrant, I go 180 degrees plus my reference angle to get that guy. And in the fourth quadrant, (360 degrees minus my reference angle. So that's how I get any angle in all four quadrants. So far, okay? Now, we spend over 30% of the class next year in grade 12 pre-calculus on this very basic stuff right here. This is where it all starts and begins going into grade 12. So we have to make sure that we get a handle on it this year so that life is a lot easier next year. Okay? All right. They have one more question that we'll look at quickly, and I'm done. An 8-meter boom is used to move a bundle of piping from point A to point B. Determine the exact horizontal displacement of the end of the boom when the operator raises it from 30 degrees to 60 degrees. Okay. So they show you a diagram at the top of the page there, right? So the first thing you want to do is solve for A here. And we know that's 8 and this is 30 degrees. Okay? Now normally, we take our calculators out. I'd ask you, where's A related to, in relation to 30? You'd say adjacent. Then I do hypotenuse, which is what? What's adjacent and hypotenuse? Cos. Okay? So that's normally what I would do, right? And then I punch it into my calculator. But you're not going to use your calculator to solve this. The cos of 30 degrees is equal to A over 8. We all agree? Yes? Side adjacent over the hypotenuse. We agree. Okay. What did I say the cos of 30 was as an exact value? Square root 3 over 2. So that means then that root 3 over 2 is equal to A over 8. Right? So I want to solve for A. Multiply that up to here. Gives me 8 root 3 over 2 equals A. That equals 4 root 3. That's an exact value. We don't want to change it. Okay? So A is 4 root 3. All right. Let's do the 60 now. Which trig ratio am I using again? Cos. Cos of 60 is equal to A over 8. What did we say the cos of 60 was? 1/2. 1/2 equals A over 8. What's 8 times 1/2? 4. That's B actually, not A. Equals 4. So the total horizontal displacement is A minus B, right? Looking at your diagram. So A minus B. What did we get for A? 4 root 3, subtract 4. That is an exact value. If you used your calculator to evaluate this exact value, you'll find an approximate value of 2.93. So if I took 4 times square root 3 and I subtracted 4, I get 2.93. Okay? But we are working with exact values, which are square roots. We're not approximating. All right? So that's it for that lesson. Okay?